Hello everyone, thanks for being here. I'm Tongshin Lee at Caltech, and I will be presenting our joint work on information aggregation for constraint online control. First, for a classical closed control system, there is typically one controller which receives states from the device and controls it by sending actions. The case is a little bit different when we have a large-scale system, because the number of controllable units may be quite large, and the central controller is often very far away from the units, and meanwhile it may be running some other jobs in parallel. Therefore, directly transmitting the actions and the states in the unit level is pretty hard. So typically there is often a local controller in the middle of the central controller and those controller units, which helps simplify the states and the actions to reduce the amount of information to be transmitted, and also decrease the computational burden of the central controller. Compared with the single controller case, the two-controller system has several challenges. First, it is very common in practice that the local controller does not know the costs, and it has to choose an action given by the central controller, and also the central controller cannot access the constraint directly. But some information about the constraints, summarized as some feedback PT, can be transmitted during the control. In this sense, each party in this two-controller system only knows part of the information, and together they need to jointly achieve some system objective, such as to minimize costs. We need to design feedback to make this possible, and what makes the problem even harder is that the coordination between the two controllers needs to be done online because of system uncertainty. Given those challenges in this work, we proposed a combination of learning and control to handle the challenges. So on the one hand, for the central controller, we redesign classical model of control to generate the required actions. On the other hand, we adopt reinforcement learning algorithm to train a local controller that outputs feedback PT. So to complete our model definition, we need some assumptions. We assume accurate predictions about the costs and feedback are available. The key assumptions of our system is that the action space is much smaller than the state space. We also assume the dynamics are more measurable, so the inverse image is also measurable. The costs are continuous, and those assumptions are only made for the ease of analysis. The goal of the central and local controllers is to jointly minimize the total costs, subject to time-varying and time-coupling constraints. Note that such a two-controller system can be found in many applications. For example, in a power system, the central controller is called a system operator and the local controller is called an aggregator. The controllable units are typically distributed energy resources as known as DERs, and there are many such kind of DERs in the future electricity network, and a typical example of such a DER is an electricity vehicle charging system. Remember, we assume the action space is smaller than the state space in the two-controller system. This is indeed true for this example. So, in a charging system, there are only a few choices of substation power levels, but there could be hundreds or even thousands of EVs, and they all have corresponding states at each time. So focusing on the actions give us a hope to significantly simplify the constraints and dynamics here. So um, with the model assumptions, we are able to focus on the side of feasible actions that contains all actions that satisfy the constraints of the dynamic system. So we need to first define an aggregation step that gives us the feedback and mentioned earlier. Our solution is that we use this maximum entropy based approach. Intuitively, we want to maximize the information sent from the aggregator to the operator. So we consider the actions as random variables and maximize the sum of conditional entropy functions of the actions. The variables are conditional distributions and they will naturally be our feedback PT. So formally, we define the optimizer of the entropy maximization as our PT, which is called maximum entropy feedback, and variables are, basically density functions defined whose domain is the action space, right? Conditioning on past actions. So given the real-time feedback PT, the MEF, we are interested in answering the following questions, right? First, do the MEF define really make sense, right? Does it have some nice properties? Second, even if it's good, right, how can we use the MEF to minimize the operator's costs? So if you remember, the operator's objective is to minimize cumulative costs in an online way, and it's not very clear how this can be done with the MEF defined here. For the first question, we show that the MEF can actually be used to guarantee feasibility. Whenever the operator selects action such that the MEF value is positive, the actions will finally be feasible. Secondly, remember that when like the MEF at each time is a density function whose values corresponding to uh, whose values correspond to the choice of actions, right? So whenever we choose an action whose corresponding value is larger in the MEF, then the size represented here as the Lipscomb measure of the size of subsequent feasible trajectories is going to be larger. This indicates that intuitively, to ensure more flexibility in the future, it would be better for the central controller to pick an action whose MEF value is large as well, even though the cost may be higher. So this may reduce the overall cost. Because the central controller could expect that in the future costs can be further reduced by having more flexibility. The proofs are based on this lemma, which shows an explicit expression of the MEF, and it shows that the MEF value is proportional to the size of a feasible set. Recall that in this work we combine learning and control to handle this two-controller system. The optimization in the definition of MEF cannot be solved in real time, so we need a way to efficiently approximate the MEF. This will later be shown in our experiments that we use reinforcement learning to train a local controller that generates the MEF PT. Now, with the feedback PT defined and its properties verified, we present our online algorithm for the central controller to minimize total costs, which is called the penalized predictive control scheme. So on the left-hand side, we first display the classical MPC with no terminal function. Note that solving this requires to know the dynamics, constraints, and states at each time tau. We propose our penalized predictive control scheme on the right-hand side. It's basically a modified version of modified control. Since we know that a larger MEF value will guarantee higher flexibility in the future, so we penalize the central controller for exhausting the controller units too much by selecting a small MEF value. Beta here is a tuning parameter that trade-offs the central controller's behavior between being greedy and preserving future flexibility. A huge advantage of the scheme versus MPC is that it only requires the central controller to know the MEF, and the central controller does not need to know any details of the dynamics, constraints, and the states. Especially, this is a significant save of both communication and computation power when the state space is much smaller than the action space. Sorry, much larger than the action space. More importantly, the feedback PT is trained from historical data, right? And it may contain some future information. Therefore, the penalized scheme could potentially achieve a better performance, although it does not know the dynamics and states, as we will see later in the experiments. The penalized predictive control also has theoretical guarantees on its performance. Remember that the MEF guarantees feasibility, right? So does the penalized predictive control. This is because otherwise, whenever the operator selects an action that makes the system infeasible, the objective will finally blow up with a positive for any positive tuning parameter beta. For the task of minimizing costs, we consider dynamic regret as our benchmark, which is defined as the difference between the online and offline costs under an adversarial choice of costs and time-varying feasible sites. First, as a converse result, what we know is that if we do not have any assumptions on the dynamic system, the dynamic regret is always linear in T. However, with certain causal invariance assumptions on the dynamic system, we can show that the PBC algorithm enjoys a dynamic regret that decreases with the predicted window size W, especially when W is an increasing function of the total number of time slots T. The dynamic regret becomes sublinear in T. And this is interesting because it gives us a non-trivial result on a very general dynamic system with both time-varying and time-coupling constraints. And this is not very well studied in literature. The definition of causal invariance looks a bit scary here, but it's actually very intuitive. Basically, we want that the side of feasible actions does not vary too much for different predetermined actions. Many time-varying time-coupling constraints actually satisfy this assumption. For example, the inventory constraints widely used in energy storage and demand response problems are causally invariant with delta and lambda equal to 1. Similarly, the tracking constraints satisfy this assumption with different constants. The intuition in the proof of the upper bound is that when we know everything from t equals to 1 to t equals to capital T, then the penalized predictive control is exactly the same as the offline optimization. So with more and more predictions, the dynamic regret is going to be smaller and smaller, and the penalty term here that contains PT can be regarded as a good action value function under the causal inverse assumption, which evaluates the cost to go based on the current action. So potentially this could be better than an MPC scheme running with no value function, as we will see next. So now let's check out how the algorithm works in a real-world application. We consider the adaptive charging network at Caltech, where we have the EV charging data recorded. The key feature of this charging system is that it has about 50 charging stations installed, but the possible charging actions in its position level is only 10. So using the PBC scheme in a system operator can reduce the number of variables in optimization by 80%. This is the workflow of our experiments. We work this through from right to the left. First, the adaptive charging network updates the states at each time by taking a charging action. In real-world implementation, this part will be replaced by real customers. After that, the aggregator uses a model trained by a reinforcement learning algorithm to approximate the MEF, and after getting the MEF and the cost, the system operator uses the penalized predictive control algorithm to get an action of aggregate power UT and send it to the aggregator. The aggregator then decides the charting actions, and finally, the charting network updates the states, and this process repeats again. As a concrete example of the operator-aggregator coordination, the operator tries to minimize the total electricity cost, and each time t, the electricity price is a varying value. The charting actions needs to be defined to satisfy the charting constraints specified by the EVs. What the operator cares is the aggregation of total power charged to all the stations. This makes our information aggregation scheme possible. In our simulation, we use data collected from November 2018 to November 2019 to train a model-free reinforcement learning algorithm and test it on a 1-month dataset spanning in January 2020. Especially, the first term in the reward function is motivated by our definition of MEF, and the last two terms aim to minimize constraint violations. With the simulation framework, we now show some of the experimental results. This figure shows the charging performance. We see that with beta increasing, the charging demands of the EVs in the testing data can be nearly satisfied. We also show the correspondence of the selected power level with the price value. We use price from real LMP data and do interpolation to obtain this smooth price function. There are two peaks in the price curve. We can see that for many days, using the penalized predictive control algorithm, the operator is able to shift some of the demands in the high price regime to a regime where the price is low. Also, the system is able to finish charging quickly before the price reaches at the second peak. In this figure, we compare with an MPC algorithm running with no terminal function. The violation of constraints is defined as the mean percentage error, which is the percentage of uncharged energy. We vary the MPE and plot the costs. We can see that with the flexibility feedback learned by reinforcement learning algorithm, even with no access to the full states of the system, the costs of the penalized predictive control are still smaller than those of the MPC. This final figure shows that when we increase the prediction window size to view, the total cost decrease. So one thing to note is because of the scalability issue in reinforcement learning algorithms, we cannot train a local controller that generates a sequence of feedback from PT to PT plus W when W is pretty large. And this is going to be an open problem for our future work. So I'm going to wrap up here by saying thank you. Please feel free to ask questions by sending me an email. Goodbye.